Okay, so now it's my great pleasure to introduce Kevin Buzzard. So Kevin did his PhD in Cambridge in 1995 in algebraic number theory, and he had positions at Princeton and Berkeley, but since 2004 he's been a professor of pure maths at Imperial. He's had some very distinguished prizes. Kevin got the White House Prize at the LMS in 2002 for distinguished work in number theory. And in 2008, he got the Senior Barrett Prize of the LMS, which is for a really outstanding piece of mathematical work. In 2017, he kind of turned his attention partly from number theory to formalization.
At a midlife crisis.
And for this work, actually, he's given a plenary lecture at the International Congress of Mathematicians in 2022. And in 2024, he started this kind of super exciting project to formalize the proof of Fermat's last theorem, which was anticipated here and we're now going to hear about. So he's going to be telling us about whether computers are going to prove theorems. Great to have you here.
Thank you. So many thanks for the invitation. And yeah, I'll do the same joke as Leo. It's an absolute honor to be giving these lectures, especially with this guy who basically has changed my life, not least by writing, forget Nintendo, my favorite computer game. It's somehow, I've always loved computer games, but the fact that I can do, sort of interesting algebraic number theory in this completely novel way is something that still blows me away. So I kind of want to think big. So the questions after I've finished, the questions maybe you want to consider. What can formal methods do for me? Many of you are probably experts in something. What can formal methods do in that thing that you're an expert in? And then more generally, what can formal methods do for mathematics? Because that's not really, formal methods have existed for decades, but that is not something that mathematicians were asking themselves 10 years ago. So these are, I think, two interesting questions. So that was the title. I had to give a title, so I wrote, Will Computers Prove Theorems? And I mentioned this on social media, and immediately some wag says that any time you see a title with a question mark, the answer is always no. Because if it wasn't no, you wouldn't have put the question mark. So in fact, the answer isn't no, the answer is yes. Like already, computers are proving theorems. And so to give this example, this thing that Leo already mentioned, a computer program autonomously solved 4 out of the 6 problems on the 2024 International Maths Olympiad. And of those 4, 3 of them, it gave formal lean solutions. So, formally verified solutions to 3 of these questions. And the other one was the Euclidean geometry question, where the system didn't use lean, it just wrote down an easily human readable and human checkable proof. And so, of course, if you're a research mathematician, you would say, well, these aren't theorems, right? These are, high school, level problems. They're not really what a mathematician would call maybe at a push they're lemmas, right? They're not really theorems, but of course, if you think that it's going to stop there, then I think you're very naive. And so really what I'm talking about is how we can, how mathematicians and computer scientists can collaborate to take these things further. Because this is one thing that really, really shocked me when I moved into this area, was that even though my background and Leo's background couldn't be more different, I can't write a line of computer code, really. I know very little about programming languages, and I'm not expecting Leo to know anything about advanced mathematics, and yet mathematicians and computer scientists are finding that they have a common language. We're stuck with a maths problem, we run into something, we can't get the system to do it, but we can ask questions which computer scientists can understand, and they can give us answers. I find this quite striking, and that we can actually communicate with each other and and make progress, even though our backgrounds are very different. This is something that's constantly, the fact that I can talk to computer scientists and they can solve my problems, even though they don't understand the maths behind it, they understand. It's a strange synergy, and one that I was very surprised by. So yeah, we've got this. Will computers prove theorems? A very vague question. Let's ask a more precise question. And the kind of question I'm interested in is, can new technology, theorem provers Leo's talked about, but language models you can't really ignore in 2025, can these things actually give mathematicians new general purpose tools? Mathematics is a very conservative area. It's really striking. When you look at the kind of things that we're teaching the undergraduates in 2025, the courses which we're offering final year undergraduates in 2025, they are essentially exactly the same as the courses that I was being offered when I was an undergraduate 30 plus years ago. So mathematicians are very slow to change and adapt, and yet there's all this stuff happening, and the question is, can we actually use it to make new tools that are of use to mathematicians? Can we accelerate mathematics? For me, I used to think that prove new theorems was the important thing, but I think that this question really dwarfs that. That traditional idea of let's accelerate maths by proving new theorems. I think there might be other ways of doing things. So, what kind of tools am I thinking of? How are we going to change mathematics? How are we going to disrupt mathematics? I like the idea of disrupting. Here's a tool. Wouldn't it be great if we had a tool where you just press a button and we can solve, all the great unsolved problems in mathematics? That'd be good. That'd be that's accelerating mathematics. So the big problem with that tool is just, doesn't exist. And it's not just that it doesn't exist. I can't see a path to that tool yet, right? It's not just that it doesn't exist, but given what we know, we don't really see how to make that tool exist. There's not really even a route to making that tool exist. That's a shame. So what about another tool? Wouldn't it be great? Now, this is some mathematician's nightmare, right? Is this a dream or is this a nightmare? Wouldn't it be great if we had a tool where you press a button and you got 10 million lines of incomprehensible code that just said, let f1 be this function, let f2 be this function, let f3 be this, Theorem 398 is that this function 28 and function 374 are related in this way. And it just goes on and on and on and on and on. You have no idea what's going on. And then at the end, it's the Riemann hypothesis. And you run it through Lean, and Lean says, yes, this is correct. That's terrifying for some, because math, what's maths about? Is it about proving all the theorems, or is it about getting understanding? Different mathematicians have different opinions about that. Do we just want to get the job done, or do we want to understand what's happening? So again, that's science fiction, right? There's no route to that yet. And so, I can't see, there's lots of new tools and it's very exciting, but these lofty goals here are kind of out of reach at the minute, But of course, 5 years ago, getting a point on the IMO was also considered completely out, right? 5 years ago, there were no language models. 5 years ago, we had Lean, we could do Lean, we could start proving, research level theorems, but we couldn't get a point on the IMO, on the International Maths Olympiad. So things do move, and they're moving pretty fast. So we don't really know where we'll be in 5 years' time. But, I don't want to just speculate. Let's talk about what's not science fiction now. So where are we? Here we go. What about a tool that can find interesting patterns? What about a tool that can spot patterns in data that humans can't spot? That would be an interesting tool. But actually, we have that tool. Right? That's exactly what the neural network does, right? We learn at high school, given a 2D plot, given x and y variables, we can plot some dots, and then we learn how to draw the best fit line, right? And then what's a neural network? Neural network, it can find best fit shapes. There aren't lines, it can find best fit shapes in extremely high dimensional data. That's what the neural network does. And so that's great. So we can give it mathematical tables that we have already, and we can say, can you spot stuff that we can't see? So there's a theorem. I just thought I would mention this theorem because Juhász and Lackenby, these are low-dimensional topologists here in Oxford, and they collaborated with computer scientists at Google DeepMind, and they proved a theorem about hyperbolic knots. And the way this theorem was discovered was that they generated a big table of invariants of knots, and then they asked a neural network to see if it could find any patterns in this table, and the neural network spotted that this sigma of k is the signature of the knot. The neural network could accurately predict the signature of a knot given other invariants. And this was surprising because the other invariants, the slope, the volume, and the injectivity radius, these are invariants coming from the three-manifold topology, the three-manifold associated to the knot. These are continuous invariants. These are real numbers, whereas the signature is an integer. So this is some theorem relating the discrete and the continuous. So it must, it must be profound. But the fact that these things were related at all, this is what the neural network told them. And once the neural network said there is some pattern, then the mathematicians took over and found the pattern and proved the theorem. So the machine didn't prove the theorem, but the machine told them where to look for the theorem. So that's kind of a surprising application. But it's really old. It's from 2021. So it's ancient. Nothing else. All the other things I cite in this talk will all be from 2024 or 2025. Because the area is just moving very, very fast. So really I want to, Jordan Ellenberg is thinking a lot about this kind of thing. How do we use neural networks, these things that can find patterns in data, how can we use neural networks to find new interesting structures, examples, counterexamples, this kind of thing. So again, this Patternboost paper, Ellenberg is a mathematician, prestigious mathematician from Wisconsin. This is Geordie Williamson, another very FRS, another very famous mathematician. Adam Wagner's a young researcher, and François Charton works at Meta. So again, a very surprising collaboration that 5 years ago you might not have expected. And they made a very simple architecture that can search for examples and counterexamples in sort of finite combinatorial objects. And what they're doing, basically, they write a naive human algorithm to try and solve a problem, to try and find extreme examples. And then they write and then they use neural networks to say, they generate lots of extreme examples, and then they encode them as strings, and then they say to a neural network, here's a lot of strings that we really like. And now can you give us more examples of strings that we're going to like? And then the neural network says, sure, I'll do that. You don't explain the question. You encode your finite graph, which is extremal in some way. You encode your finite graph as a string. You give it the neural network, say, I love these strings, give me more strings. It says, sure, I'll give you strings. And then you try and decode the strings back to graphs, and half of them just don't decode, they're garbage. And then the other half do decode into graphs, and then you look at these graphs, and there are other great examples, but they're not extremal. You can keep adding edge, you can do more. The computer and the human are just thinking about the question in really different ways. And they find, they can find counterexamples to theorems this way. It's very weird. It's an extremely simple to read paper. I'm quite excited. This work of Ellenberg, you should look at recent work of Jordan. He's also collaborated with the physicists from Oxford, getting machines to write Python programs which are solving maths questions. It's a very surprising and innovative new use of technology. But the big problem with using neural networks to do this kind of thing is that they have limited application. You can't. If you're interested in an area of mathematics where there are lots of tables, or where the fundamental objects can be described by finite amounts of data, and the interesting problems is finding new data, then that's great. But if you're doing research in Sobolev spaces, or whatever Banach manifolds, or intrinsically infinite dimensional objects where there aren't any tables, then you just might not be able to use these tools at all. So they've got limited applicability, and that's just the same. We've seen that happen before, right? In the 1960s, in the 1970s, computers became available to mathematicians, and they were just very, very fast, fancy new calculators. And all of a sudden you can multiply two 100-digit numbers together really quickly, right? And if you're doing research into Banach manifolds, there's no use to you at all. But if you're doing research in sort of computational number theory, then suddenly you've got a great new tool. So we've seen, computers come along and they might affect some bits of maths. They might make some areas there's suddenly an exciting new thing. I'm interested in general purpose tools. This is the kind of question. Can we really give mathematicians a general purpose tool? So now we have to talk about, I'll talk about theorem provers in a bit, but we've got to talk about language models. Because, any mathematician who's used them will know that right now they are not perfect by any means for doing mathematics. So the mathematicians are there any mathematicians in the room who've actually used the language model and it's told them something useful? Are there any? Can anyone put their hand up to the? There you go. So some, you see, there you go. Great. There's like 10 hands. You see, but the AI people are really, really excited about language models, but they're in their current form, they're not perfect. So actually, I used ChatGPT last week because as has been mentioned several times, I'm currently involved in some strange project related to Fermat's last theorem, and if I click this, then all manner of things would happen, right? I'm going to try clicking this. So anyway, as I was saying, there's some website on the internet that contains a whole bunch of maths involving some kind of it's a very beautiful website. It looks really nice. Rendered in beautiful LaTeX on the web, where I'm just in the middle of writing a very long an explanation of a lot of mathematics behind Fermat's last theorem. And I needed the fact that if A was a Dedekind domain with field of fractions K, and if L was a finite separable extension of K, and B was the integral closure of A in L, then I claimed that for an arbitrary K module, tensoring over K with L is the same as tensoring over A with B. So there's some random statement in graduate level algebra. And that's the kind of thing that I thought that I should be able to prove. But the problem is I just got a bit stuck because if ring of integers of a number field, ring of integers of a finite extension, the new thing might not be free over the old thing. It's going to be projective, but it might not be free. It's locally free, but maybe not free. So that held me. There was some technical issue. So I thought I should be able to do this, right? And I spent like 2 minutes on it, and I was just like, this is stupid. This is graduate level algebra, right? Okay, so so what would 20 years ago, I would have just knocked on another number theorist door and said, how do you do this? 10 years ago, there's a new option. I could ask on Math Overflow, right? Or math.stackexchange. 2 years ago, I could just kind of cheat and ask on the lean chat because there's a bunch of mathematicians hanging out there. And it's likely that somebody will give me an answer quickly. But now, of course, you can actually ask ChatGPT for it. I don't pay for these things, right? Because I'm super skeptical that they're useful. But you just go to chatgpt.com and I type in my graduate level question in commutative algebra. And the answer is illuminating, right? Because I asked this explicit question about tensoring up finite extensions of rings of integers of number fields. And the first thing it does is it says, it suffices to prove this simpler problem. And that was something I'd spotted when I was thinking about it for 2 minutes. And I thought, this looks like progress. And then I decided, actually, is it progress? The reduction seems just as difficult as the original question. So I tried that, and then I gave up on that, and then I asked ChatGPT. And the first thing ChatGPT does is finds the same reduction. And then it actually, gives the idea which I'd missed. It gave the idea about how to prove the reduction. And then it justified its argument with rubbish. This is it's very, very wishy-washy on exactly how this proof worked. But the thing is, it gave me enough clues that I could actually put everything together. And so there we go. So the language model was good in the sense that it pushed me in the right direction, but it wasn't perfect. Because when we came to the details, it was not at all, as I say, it's not an inaccurate summary, right? The details were vague or meaningless. And why is that happening? It's because, of course, they know all the facts on the internet, right? That's how they're trained on the internet. But the thing is, they're not very good at logical reasoning, right? They're not very good at actually, they don't have understanding in the same way that we have understanding, right? Can these things think? It's just not even a meaningful question. It's like asking if a submarine can swim. Humans think. These things are not thinking, they're doing something else, right? As Ken Ono, this is a quote from Ken Ono, right? It's not cognition, they're doing recognition, right? They've seen lots and lots of things before, and so they kind of think, oh, I've seen this thing before, that's what humans do in this situation, I'll do that. And actually, it's interesting, like what mathematicians actually doing the same. A lot of what mathematicians are we just doing pattern matching? Occasionally we have ideas, but how often are we having ideas, and how often are we just, just going through the motions and, I know, just applying stuff that, we just, it's not immediately clear how many times we're having brilliant new ideas and how many times we're just applying facts and techniques that we just know work because we've seen them in other situations. So we're maybe doing similar things to the machines, but the thing is we can back it up with this logical reasoning. We take an idea from a related area, but then we can rigorously prove that idea works in our situation. Whereas a machine takes an idea from another area, attempts to apply it, and then it's really fluff when you ask them, does it actually work here? This is the thing. They never say, I don't know. The common failure mode, if you ask a human a question, a common failure mode is, I don't know. Whereas you ask a machine a question, the common failure mode is bullshit. This is they would rather make something up than say they don't know. So this is the big question, right? If we want to use these things, how do we teach language models to reason accurately? And the way that we're going to do that, computer scientists, they like challenges. They want a challenge, and then they want to be state of the art in that challenge, right? And if you can get state of the art, you can get a paper. That's how computer science seems to work. You make some challenge, and then you say, and AI can try this challenge, and at the end they get a grade. They get a grade. They try this challenge and they get 15%. And if that's better than any other AI, then they've got state of the art. And if you get state of the art, then what you win is a paper. That seems to be how computer science works, as far as I'm concerned, anyway. So how do we make challenges? The way you make a maths challenge is a data set, right? So a question, a big collection of mathematical questions. That's what a challenge looks like. And the idea is you get the machine to answer the questions correctly. You get a point for each one you get right. And so now the question is, what do mathematical data sets look like? Because when you're a mathematician, these things are being generated by computer scientists, and as mathematicians, we tend not to look at them at all. So what do mathematical data sets look like? They come in several forms. They're mathematical questions, but what level? Right? They can be sort of GCSE level, right the way up to research level. That's that's the range of the mathematics. Really, really extreme. They might be in natural language, or they might be in a formal language, like Lean. We've just seen there are other formal languages as well. But of course, Lean seems to be winning. There's in many cases the formal language chosen is Lean for mathematics, at least. The problems might have shorter, this is a big difference. The answers to the questions might either be expressible in about 8 characters. There might be a multiple choice question, or they might be, what is this number? Or they might have really long answers, prove this theorem, and the answer is like 2 pages long. So you get different data sets ranging, the kind of answers you get can be very different. And finally, they can be either public or private. The private ones, the way it works is you have 100 secret questions, and they say, we've got 100 secret questions, and here's 5 of them. We'll make 5 of them public, and the other 95 are secret. So you get some kind of feeling as to what the data set looks like, but you can't see. You can't see the question. If you want to have a go, you have to send your AI to the company or to the organization that's holding the secret questions, and they run it, and then they give you the report about how many you got right. So let me just give you a couple of examples of data sets. This is the Artificial Intelligence Maths Olympiad. This is Gurko, who was mentioned in the last, is a guy who's funding more and more mathematics via XTX markets. So there's he's really pushing the idea of open source AI. He's very worried that the sort of closed source. I was talking about, wouldn't it be great if we had a general tool that helped mathematicians? But one thing that perhaps would be a bit less great if that tool was owned by a private company and they was like, just for $1,000 a month, you can have that. Your university can have that tool. He wants to see open source tools. So that I should say, I mentioned this first. I'm on the advisory board for this project. So right now we've had 2 progress prizes. So we've had 2 competitions, and both of the competitions have involved private data sets, so secret questions, and the questions are written in English, and they're sort of challenging high schooler type questions. Not as hard as International Maths Olympiad, but there are other Olympiads at easier level, right? And the key thing is the answers are short. Right? Answers are always whole numbers between 0 and 999. And this is the kind of question that you see. So it's not the kind of thing you can do immediately. So each of the 3-digit numbers from 111 to 999, you colour it blue or yellow, and there's some rule. And then the question is, what's the maximum number of yellow? So it's sufficiently big, you can't solve it by brute force. You can't do all 2 to the 889 possibilities. You have to, start. So it's a sort of a combination. There's some calculation involved and some reasoning involved as well. And we're at the stage now where you can type that kind of question into a language model, and the language model can get it right. So, as I say, the questions are kept secret, and if you want to play, then you have to give us your model. So you can't. We won't send the questions to the private models. You have to upload your model to to Kaggle, and then Kaggle run it and tell you what you got out of 50. And there's prize money, right? The models compete to win 6-figure prizes. And there's been 2 competitions so far, and the second one just finished. And top of the leaderboard was a gang of 3 or 4 people, and they scored 34 out of 50. So it's sort of a high school Olympiad. There's state of the art for these kind of high school Olympiad questions as far as open source models are concerned. If you asked OpenAI to do this, they would probably get a much higher score because the closed source models are always ahead. So one advantage of me being on this, me being on the organisation committee for this thing is that we get to see secret data that's. So this is a table. These are the 50 questions. As I say, this competition's just finished. And then these orange bars indicate sort of the 10 most popular answers. These are the top 500 AIs that took part in this game. And the light orange is the most popular answer, and then the dark purple is the least popular answer. And so you grade it from light orange to dark orange, and then the grey is all the other answers. And then you take the most popular answer, you colour it in green. So that, of these 50 questions, the top question, they're the easiest question. You can see like 90% of the models were guessing the right answer first time. Then then by the time we're halfway down, you can see it's still the case that the most popular answer was equal to the correct answer for the first 50%, and then you see things are going wrong, right? These things where there's very small green dots, or the green stripes there indicate like the 8th most popular answer turned out to be the correct answer. So there, there's some data, but basically 500 language models are getting half of these questions correct. So there's some kind of idea as to where open source AI is now. But we don't care about these stupid undergraduate questions, right? We care about hard questions. So what about this FrontierMath data set? Here's a proper question. Here's a question about moduli spaces of conics. So, here's some enumerative geometry question. Well, it looks like an enumerative geometry question. It's actually a combinatorics question, which is heavily in disguise. But you've got moduli space of conics tangent to a given set of 5 conics in the plane. And the question is, and now you look at this moduli space mod P, and you ask how many connected components it's got. And as P varies, this answer changes. This is not over FP bar, over FP, so this is an arithmetic question, not a geometric question. And then the answer is give the answer to 2 decimal places. So again, the answer is very short, but now this is research level mathematics. And one of OpenAI's closed source models has got 25% on this data set. So we've got questions of that nature. That's technical and complicated, but the AI is getting 25% on that, including a correct solution to the question there. So that's where closed source is right now. But when you actually ask it, this is the problem. It's great. The model can solve that. The model can get that number right. But then when you ask it to explain why that number's correct, it's wishy-washy. Because it makes them get. It has to we've got some Galois group and it has to guess what the Galois group is. It just guesses the Galois group as the full symmetric group, and it's right. And then you ask it, why is it the full symmetric group? And it's vague. It doesn't actually know why, but it's just, it's just. This is the problem with these number questions, is they don't correctly test reasoning. They test how good you are at guessing the answer. And these models have got very good at guessing the answer. So the closed source models are around 2 years ahead, and the closed source models are trying to pull ahead because the tech companies have stopped publishing. This is what's happened, because they want to stay ahead, and the open source models are trying to catch up. So why are these data sets private? Well, it's kind of obvious, because if they weren't private, if you just put them all on the internet, then people would start asking them on Math Overflow, and people would start answering them, and then the answers would be on the internet, and then the models would learn the answers, and then the models would just all get 100%. So it would break the system. And now, why are the answers numbers? That's a much more pertinent question. Why are there numbers? It's because we want to be able to mark it really easily, right? If you ask a question, and if you ask how do you prove this theorem, if the answer is a 2-page long proof, who's going to mark that, right? You can't have AI marking its own homework. This is the problem, right? If the question is prove this theorem, and the question's in English, and the answer's in English, you see where this is going, right? If the question's in English and the answer's in English, and the answer is 2 pages of LaTeX, and we have to decide how many points out of 10 this answer gets, a human has to read it, right? And that's really expensive, right? So the computer scientists want to get state of the art, but the problem is marking a proof, right? That's what we do, right? We don't ask, what is this number? We ask how to prove this theorem, but it's too expensive to mark that in natural language. So the natural language data sets are all what is this number questions, right? And that's not what we do. Okay, so formal data sets, right? And these are data sets. Now it's different. Now the questions are not written in English, they're written in Lean. All these other languages, but for the vast majority of them are written in Lean. And now, of course, you can ask the interesting question. You say, prove this theorem, right? And now the idea is this time, now the model writes a solution, and now we just throw it into Lean and see if it compiles. Because now a machine can grade the answer. right? If it's wishy-washy, it's just not going to compile, right? That's what we do. And now, of course, the big problem, unfortunately, is that right now the level is terrible. The level is terrible, right? The data sets are mathematically trivial, right? So we have these formal data sets where the questions are in lean, but they're GCSE. They're really very, very easy stuff. So the hardest one I'm aware of currently for these formal data sets is Putnam Bench, which is formalized statements of 640 Putnam questions. So the Putnam is an undergraduate level problems. So hard undergraduate level problems. And state of the art is abysmal, right? State of the art is 10 out of 640. So that's good when you see state of the art like that, because it means there's plenty of room for improvement. Well, by the time the state of the art is 60%, then you've lost interest. Like people are like, oh great, I've got 65%, but like if you're solving half the problems, then it won't be. Give us a year and you'll have solved all the problems. But right now, this is undergraduate level material, formalized in lean, and people can't do it, right? Apparently, OpenAI's most recent, this is this Chinese model, DeepSeek Prover, are claiming they've got more than 10, but it's yet to be, and the Putnam people have to officially check this. But apparently, there's been a big jump this week, so we'll wait and see. But what do we really want? Like, what am I trying to sell here? I want these systems to do the kind of mathematics that I want them to do the p-adic Langlands program, right? That's what we want, and because that's what's happening in places like this. And so data sets are private, that's a bit rubbish. Like data sets are too easy, that's a bit rubbish. So there's a very good paper by Simon Frieder again, talking about the general problem of mathematical data sets and just flagging all the things which are somehow insufficient currently. But I do believe that when we get it right and we start making data sets that are actually correctly modeling the kind of mathematics that researchers are doing, you will get computer scientists trying to get state of the art on these data sets. Right, so where are we? Like language models are rubbish, language models make stuff up, current data sets aren't asking the right questions, and so now let me finish this talk with a vision that isn't science fiction and is maybe a route to some kind of tool that mathematicians can use. So let me go all the way back to 2023 when language models had first appeared and they couldn't compute, right? And it was really funny, right? You ask ChatGPT to multiply two 10-digit numbers together, you give it two explicit 10-digit numbers together, and it confidently gives you a 20-digit answer. And it begins in the right number, and it ends in the right number, and in the middle all the numbers are just made up. That was what it looked like in 2023, right? But in 2024, when you ask it to multiply two 10-digit numbers together, it just fires up a Python, it fires up Python, it asks Python what the answer is, and then it reports the answer, right? Because these systems learned how to write Python code. And how did they learn how to write Python code? Well, they just trained them on Python. There's billions of lines of Python code on the internet. So the language models just train on that Python code, and then they got really good at writing Python. And now when you ask them computation questions that Python's good at, it just gets Python to do it. But right now, as I've said several times, they can't reason at a high level, right? And the harder the mathematics gets, the worse they get at reasoning. Okay, so maybe we should just teach them to write lean code. That would be good. Because then, that stops them bullshitting, right? You ask them to write, you say, prove this theorem, and then internally it proves it in lean, and then it translates it back into human, it's going to get it right. But the problem is we can't train it on lean code because there's only millions of lines of lean code. And a lot of that is undergraduate level, right? This is the problem. We want to break through we want to get them to do research. We want to break through undergraduate level, and most of it is undergraduate level. So undergraduate level, that's great. DeepMind has shown us that you can train on what's already there, and you can get half, you can solve 50% of the 2024 IMO, given only what we have. But as I say, that's lemmas, right? That's not theorems. So how are we going to get this further? And this is a big problem. We need to think seriously about getting a lot more modern mathematics formalized. It seems to me this is the problem. We need to get a lot more modern mathematics formalized, and because this is not science fiction, right? Maybe we can get machines to do that. Maybe, because it's one thing coming up with your own ideas, but actually translating from a human proof into a computer proof, that really does not sound, that's much easier than coming up with your own proof. Just doing we can translate between English and Chinese, so why can't we translate between English and Lean, right? That doesn't sound crazy to me. And of course, people are thinking about this. And so finally we're there. This is one of the reasons why I'm currently teaching linear proof of Fermat's last theorem. So this was proved in the 1990s by Andrew Wiles, and ably assisted by my advisor, Richard Taylor. The proof is huge. The Wiles paper is 100 pages, but it's got 80 references. Leo said the proof was over 200 pages. I think if you were to write down the proof, from the axioms of mathematics, it would be more like 2,000 pages. I think it would be a more reasonable estimate of how long this proof is. And the weird thing about the proof is that Fermat's last theorem is a question about positive whole numbers, but the proof goes through all manner of really complex structures, right? All these modern buzzwords, elliptic curves and modular forms and Galois representations of finite flat group schemes, and we've got them all, right? There's an example. Those are examples of things that over the last couple of years we've now carefully formalized these things in Lean. So now, it's in my Fermat's last theorem repository, and it slowly moves in. My repository is a feeder repository for MathLib. So elliptic curves and modular forms are in MathLib. And the other two things, Galois representations and group schemes, they're not in MathLib yet, but in a year's time they will be. That's how the project is going. I'm building stuff, but when we make a new definition, we make sure it works, we make sure it's usable, and then when we're convinced we've got it right, we push it. But it can't just be me, right? It can't just be me doing Fermat's. There's more to maths than Fermat's last theorem, it turns out. There's other areas of mathematics. And here are just some dumb examples of stuff that's like undergraduate or beginning graduate level mathematics that are not formalized, that are not formalized in, as far as I know, any theorem prover. And they just need someone to sit down. It's not difficult to sit down and teach the machine. It's not just the definition and basic facts about the definition, right? But the thing is, we can get machines to prove theorems, but it's really difficult to get machines to write down definitions, because formalizing definitions is an art, right? It's system specific, right? Well, the best way to teach Lean what a knot isn't necessarily the best way to teach Isabelle or to teach MetaMath, right? It's system specific. And also you've got the problem that the machine isn't holding your hand at this point, right? The machine will check that your definition is syntactically correct, but the machine won't check it's semantically correct. The machine won't check that you've written down the right definition. The machine will just check you've written down a definition that makes sense. So you've got to be super, super careful here. So this is something that human experts need to do, right? The theorems, we can let the software do it itself, right? In 2 years' time, maybe the systems will be translating from human maths, translate a human proof into a Lean proof. That is absolutely not out of the question. But for me, formalizing definitions, you absolutely need to take anything a machine says with a very big pinch of salt, right? So who is going to formalize all these definitions in all the graduate courses that are being run in Oxford, right? It's not going to be computer scientists, okay? Whose job is it? I mean, I claim that it's the mathematics research community's job, right? We've got to do it. We are the people who are qualified, but the problem is we're not going to be rewarded for that, right? The reward system in maths is that you get points, you get money if you get points in the research assessment exercise, and you get points in the research assessment exercise by papers, and you get papers by proving theorems, new theorems, built upon old theorems, which are built upon old theorems, not all of which are correct, as I found out when I was trying to teach a computer a proof of Fermat's last theorem. We're not as smart as we think we are. So we've got this idea that everything in the literature is fine, and we just need to build more, right? But is this really how we're going to change mathematics, right? I think that this AI and theorem provers are together, they are giving a completely new way of thinking about mathematics. But the system isn't, the system, there's something wrong, right? That's the problem. If actually, what can formal methods do for mathematics? Can they really turn it on its head? I mean, that's it. Thank you.